Hi, and welcome to our 10 a.m. press conference, Puerto Rico 1 year later, Hurricane Maria's lasting footprint. Our speakers this morning are Maria Uriarte from Columbia University, Bill McDowell at the University of New Hampshire, Doug Morton from NASA Goddard Space Flight Center, and Miguel Roman from NASA Goddard Space Flight Center.
Good morning, and thank you for coming to the press conference. I'm going to start by telling you a little bit about what Hurricane Maria did to forests in Puerto Rico. And of course, we care about these forests because they sequester carbon, stabilizing climate, they prevent soil erosion, and they're also home to many species. We don't come into this from a historical perspective. In fact, we have been studying forests in Puerto Rico for 30 years under the auspices of the long-term ecological research program of the LTER. And since we started studying these forests in 1990 or thereabouts, there have been 3 severe storms that had hit the island. Hurricane Hugo in 1989, Hurricane Georges in 1998, and the most recent, of course, Hurricane Maria. Hurricane Maria is of a very different nature than the 2 previous storms. But what these events have given us is, first of all, a long-term perspective on what hurricanes do to this forest, and also a baseline against which to compare the impacts of Hurricane Maria. So what we did after the last severe storms is we went to a series of plots that we have distributed throughout the island. And these are here in the red circle is a Yunque National Forest, which is the site of the long-term ecological research site, but also to a series of plots that we have throughout the island in black here. And we went back and we measured for each tree how much damage it had experienced. And then we were able to couple those observations with remotely sensed data from Landsat to essentially get an island-wide assessment of the type of damage that Hurricane Maria did. So we estimate that about 30 million trees were either killed or severely damaged in the storm, and also that there was a biomass loss of about 11.5 billion pounds of carbon. What was interesting is that we went back and we also wanted to understand what were the factors that determine risk in this storm. And so, not surprisingly, these bars here are so important. So a bigger bar means that that variable was most important, right? Clearly, bigger forests generally lose more biomass because there's more biomass to lose, and also they are more prone to damage. What was really surprising was that the second factor after canopy height or biomass was not wind, which is what we tend to think about when we think about hurricane damage to forests, but rainfall. And the importance of rainfall was further confirmed by the fact that antecedent rainfall, that is how much rain had fallen in the previous week, coupled with an index that we have of soil wetness, were also important factors in determining damage. Furthermore, we estimated topographic exposure, and areas that are typically protected in valleys and in leeward sites actually were not protected at all in this storm. So it seems that the risk factors have shifted from what we have traditionally thought mattered for landscape level damage. So this tells us something about risk factors on the landscape scale, but what about species composition? For that, we need to go back to the long-term ecological research site where we have been studying forests for many years. And this set of graphs here show on the x-axis the mortality, uprooting, and tree breaks that we saw in Hurricane Hugo. Georges was very similar, so I'm only showing Hugo here for the sake of comparison. Each one of those blue dots is a species. And so if the effects of this storm were the same as those of previous storms, all of those dots should fall on the 1-to-1 line. And as you can see, they don't. So we saw in Maria slightly elevated mortality rates, but not anything that was very dramatic. Very similar rates of uprooting, and that was interesting. But what was strikingly different is that we saw 2- and 4-fold increases in the rate at which trees broke. And we're still trying to make sense of this. We don't exactly know why this happened. But that dot that sits on the 1-to-1 line, which I have here identified with the green arrow, is the palm, a native palm, the Sierra palm. And that was the only species that really behaved in the same way in both the storms. And so we expect that eventually this will become more dominant because many of these trees that broke will die a slow death over the next couple of years, because we know that from our experience studying storms in the past. So this is interesting because climate change, as you know, is making hurricanes more destructive. And we're expecting increases in maximum wind speed anywhere in the range from 2 to 11% by the end of the century. And even with a greater certainty, we are expecting increases. Actually, there's been a couple of papers on this recently, increases in the order of 20 to 30% in the amount of rainfall associated with the storms, right? So what does this mean? Well, the take-home points that we have so far is that storms of Maria's characteristics of the severity, both in terms of extreme winds and rainfall, have very different impacts on forests than those that we have observed in the past. Rainfall, in this last one, was the predominant driver of landscape damage, and yet, typically when we have thought about impacts of storms on forests, we have focused on wind, and so this really talks about the need for focusing on rainfall as just as important factor. These severe storms also have some very clear impacts on forest composition with winners and losers. In particular, you can see here in this picture that was taken after the storm just how predominant the palm is, and this is everywhere, in the Yunque National Forest in particular. And we have done some modeling to indicate that in terms of carbon, what this will mean, and I will talk about this on my talk on Friday, that these forests will go from being essentially carbon sinks to being carbon sources. So with that, I am going to pass it off to my colleague Bill McDowell, who is going to talk about impacts on streams.
Thank you, Maria. It's a pleasure to be here and tell you about the impacts of a hurricane or a fire drill on one's ability to focus and make slides go forward. What am I doing wrong, please? Okay. Thank you very much. This represents the latest update in a long-term collaborative project funded primarily by the U.S. National Science Foundation under the auspices of the Critical Zone Observatory program, the Long-Term Ecological Research, LTER program, and the Macrosystems Biology. And I'm going to focus today on the results specifically before and after these two hurricanes, Irma and Maria, that you've already heard described by Dr. Uriarte. Folks, I'm trying to go forward.
Here's the pointer.
Okay, we'll do it this way. Thank you. So, the focus of this work is to understand how what happens on the landscape affects what's delivered downhill. Now in Puerto Rico, downhill is a coastal zone and is quite close to the mountains. And we know from decades of work that what's delivered from the land to the ocean can really make a difference in the health of coastal ecosystems. Too much of a good thing, too many nutrients, especially nitrate, can affect the health of coastal ecosystems. We see here a plume, shown in the green, of algae moving north from Delaware River to Long Island. Well, we know that this phenomenon is important. Now we want to look at what's happening in our tropical rainforest sites in Puerto Rico. And so the mountain is shown on your left, and one of the streams that we've studied for many years is on your right. We've actually been looking at these streams for 35 years now and have the longest record of stream chemistry in the tropics with that sort of a frequency of sampling. So hurricanes are a big factor in the Caribbean in terms of structuring vegetation, and as we've seen, affecting stream chemistry. In 1983, the top of the mountain looked like this. A few weeks after Hurricane Maria, similar high elevation site looked like this, with extensive damage and now newly visible streams that are coursing down the mountain on their way to the sea. So how do we determine the effect of these large disturbances to the landscape on stream chemistry? It's difficult because the streams, as you can see here, can reach really high concentrations, high discharges, a lot of water in the stream, and yet on average, they're typically much lower flow, as we see on the left in this slide. So to do this, to measure across the full range of discharge conditions, we're now employing the latest sensor technology that can measure nitrate concentrations directly. We put them in this protective cage, which you see on your right, and beneath it is actual sensor, which is deployed in the field. So when we deploy this sensor, what kind of results do we get? I show here the concentration of nitrate, this important nutrient, measured every 15 minutes in 3 or 4 months before the hurricane and the full year after the hurricane. As you can see, I've labeled Irma and Maria as the vertical bars, and we want to walk through some of the important lessons from this 15-minute record. First, we see this period of very stable nitrate concentrations before the passage of the hurricanes. Next, we see this elevated baseline, a new normal following the hurricane. Finally, we see this extreme variability. Basically, the wheels have come off the bus. Instead of being stable as before the hurricane hit, stream concentrations are now going up and down wildly in response to individual rainstorms. Third major point, though, is that is now declining over time, so we seem to be reaching a new period of relatively constant, though elevated, nitrate concentrations. So if we look at this response to the storms in detail, this is something that's never really been documented before, with the change in the behavior of a solute like nitrate in response to a major disturbance. We see the following. On the left, the red balls moving through the storm. This is the stream height and the stream volume of water over time. So we see a sharp peak as the rain moves through the system. On the bottom, before Maria, the green line, and the trajectory through time during the storm before Maria. It's flat. There's no real response to a rainstorm. Similar magnitude rainstorm after Maria, and we watch the ball going through. All of a sudden, we see this very large increase in concentration during the storm after Maria. So where does this take us? If we look at the implications, first, we've documented over the last 30 years, everyone has seen that we have many more hurricanes of significant size than we've had in the past in the historic record. So hurricane frequency has at least increased over the last 30 years, and we expect it may well increase in the future. So this means that the connections between the land and the sea will become more and more important after these large storms. On the left, you can see a river near San Juan discharging into the ocean a few weeks after Hurricane Maria. Second point is that nitrate is increasing. We've documented a larger increase, and it seems to be lasting longer than we've observed in past storms. So that the magnitude of the nitrogen delivery from land to sea is larger, and with that then we expect an increased risk of harmful algal blooms that can smother the coral and cause dead zones in the ecosystem. So I'll leave it at that, and we'll turn it over to our colleague, Dr. Doug Morton of NASA, who tell us some more about island-wide impacts and the structure of the canopy. Use that. Don't use the mouse.
Thank you very much. As we've seen from the ground perspective, Hurricane Maria had wide-ranging and severe damages in terms of vegetation and the alteration of the way that vegetation controls water flows across the island. In this work, I'm going to take you up a scale as we look to use our airborne information to connect the dots of those field and location measurements, understanding island-wide damages from the unique perspective of an airborne laser system. So this is some work in collaboration between NASA scientists and our colleagues at the U.S. Forest Service. It's funded not just by NASA and U.S. Forest Service, but also the Department of Interior as they look to assess the characterize damages to habitat, infrastructure, and the larger island network. This is work that leverages our airborne package, which is a combination of a lidar, a hyperspectral, and a thermal system. And I'll show you some examples from that here. In tropical rainforests, gaps are the main currency of change. So you can see from this schematic on the top, essentially the loss of one large canopy tree frees up growing space for shorter, new trees to move into those spaces, and that mosaic of habitats is what creates such a diversity of environments for a wide range of species, both plants and animals. One of the things that we can do from an airborne perspective, especially using some of our laser technology, is we can actually know how many trees fall in a forest, even if no one is watching. And so we can ask these questions which have plagued us as ecologists over time, for how common these gaps are, and then how do they vary if we look at an area like Puerto Rico before Hurricane Maria and after Hurricane Maria. And so the main points here of my talk are that under normal conditions, gaps are pretty rare. They're quite small, and they end up yielding only very dark places for new plants to regrow or surviving trees to continue to fill those spaces. But in Hurricane Maria, we saw that the hurricane created about 30 to 50 years worth of gaps in a single day. So, using our airborne lidar technology, as we fly along in an airplane, low and slow, we fire 600,000 laser shots per second. That laser energy is intercepted by the top of the canopy, by branches in the understory and top of canopy, and the ground surface, and that allows us to create a three-dimensional model of these forests. That's fundamentally changed the way we understand and change processes in a three-dimensional context. It's also given us access to make very detailed and precise measurements of changes in the height and structure of forests over time. We were actually in Puerto Rico before Hurricane Maria. The island was almost completely deforested in the 1930s, and so what remains today are a patchwork mosaic of different second growth forests that have recovered after land abandonment. And so we're curious in understanding how those forests have recovered over time. That gave us an opportunity, using the areas here in yellow, to assess where those changes, how those same types of forests, from young to old second growth forests across shallow limestone soils up to the top of the Central Cordillera and the top of El Yunque, how do those same forests respond over time? And as we compare what happened before, and our three-dimensional models before the hurricane on the top with what happened after the hurricane on the bottom, you can see that the storm came through and literally gave the forest a haircut. The forest lost 1/3 of its height, and it opened up to more than 10% of this forest, which was normally a closed canopy, tall, multi-layered tropical forest, 10% gap straight to ground, which you can see peeking through there in those lighter colors, which is a real change in the size and the frequency and the amount of light and nutrients on the forest floor that really is going to govern the way in which these forests respond over time. So we saw that across the island, about 55% of the canopy was damaged. And there really was no place to hide, as Maria highlighted before. We saw that same level of damage on the top of ridges, on slopes, and in valley bottoms, which just means that the strength, severity, and duration of this storm was enough to create those kinds of damages across a wide range of forest heights and forest landscape positions. So looking forward, if we can look forward. Try one more time. Might have frozen everything with a large video. If I did, that's fine, I'll go audible. So looking forward, I guess there's sort of three main takeaway points from this. One is that we've obviously been able to characterize at a landscape scale what a reset this hurricane was in terms of the forests of Puerto Rico and their structure and composition. We've also been able to evaluate in more specific three-dimensional detail how this storm event created winners and losers. We are also able now as well, I think this is really critical to point out, despite the fact that we're focusing today on the amount of damage to these forests, these are natural ecosystems that are incredibly resilient. And so what we see essentially is an incredibly productive environment. We've freed up a lot of growing space, we've freed up a lot of light and nutrients, and that's led to a rapid pulse of regrowth across the island. And so this isn't the end of the story for Puerto Rican forests, this is just a major change event which has changed the trajectory over time. So I'll leave it there and pass it on now to my colleague Miguel Roman for an even broader scale look at the island and its response to the storm.
Thanks, Doug. So today what I'm going to do is I'm going to talk about how NASA's Earth Science program devoted some time looking at the disaster of Hurricane Maria in the context of lifelines affected, particularly looking at the energy sector. So I'm going to show you some pictures of how we map power outages from space and how we've been doing that since the very beginning. I like to put this image here of our black marble image created by the Earth Observatory because when you think about a disaster, this is the kind of image that absolutely comes to mind first, which is the eye of a hurricane going through a target and looking at the impact. And there's a lot of data that goes into generating an image as beautiful as this. And there's a lot of information that can be gathered from this kind of maps, information about hurricane wind speed, precipitation, how that leads to additional cascading failures like flood impacts. I want to acknowledge the Disasters Program and the Earth Science Data and Information System for helping us carry on with this work in the last year. So we're talking about resilience. I want to talk about resilience in terms of community resilience. So what are the actual human costs of Hurricane Maria? This is some statistics from our partners at the Puerto Rico Conservation Trust, looking at the actual damage to just lifelines, the living conditions of people across Puerto Rico. And what we're trying to do at NASA is try to understand what is the data that can be turned into information to help improve human decision-making in the face of more increasing and intensive risk across island nations and territories where this is going to be the new normal. You know, we're going to expect another Hurricane Maria in a year, in 2 years, in 5 years. How are we developing strategies from an earth science perspective to provide the data and the tools to understand risks in all its dimension, not just the impact, but also looking at exposure, where the buildings need to be in the future, and looking at vulnerabilities, looking at historically disadvantaged communities and how will we look after them during these events. And so a way that we do this is using nighttime lights at night. So this is an animation that looks at this is an animation that looks at the trajectory of Puerto Rico Hurricane Maria from GO16. And then we use a new product that is being launched in the new year called the Black Marble. This Black Marble data is then integrated with harmonized Landsat Sentinel-2 imagery generated at Goddard and with OpenStreetMap data to locate the extent and the duration and magnitude of power outages throughout the entire transcourse of recovery. And so we did the study for up to 6 months, and we stopped at 6 months. And what I want to show is kind of the results from an island one perspective, and then downscale it all the way down to individual communities. And the results look like this. So there are two plots in here. This is Puerto Rico's energy sector, shown from two data sets. The black is the official reports from the Department of Energy. And you're seeing is right here is the aftermath after Hurricane Maria, where 100% of the island goes without power. And what you're seeing here is energy output being restored. So these are the power plants coming back online. On the red, you're seeing the customer side of things as being reflected from the night lights data. So as people turn on their lights, we are able to document that from 500 miles in space. So these two are very complementary data sets. They're not supposed to be looking after each other. And what I want you to pay attention is that there is a lag between the official reporting, which shows power plants are coming back on, and the actual number of customers that have power. And so by looking at this, we can actually complement existing surveys to understand and track the location of vulnerable communities in Puerto Rico. And we can not just do this for the entire island, we can do this for individual communities. So these are 4 of the 78 municipalities in Puerto Rico. And we start mapping municipalities that are adjacent to each other. So we're looking at Arecibo in the north and Ciales right next to each other. This is a residential part of Ciales that exhibited mudslides. This is the mountaintop town of Adjuntas, the coffee growing region, which did not get any power for almost a year. And so this is Ponce, which got which will had a more resilient infrastructure in its central district, so you can see recovery coming back. Overall, what we see is that over 41% of rural municipalities in Puerto Rico had these long duration failures without electricity for more than 6 months. In contrast, 21% of municipalities in urban areas saw equal longer periods without outage. So there's this large discrepancies and inequities between urban areas and rural communities this is kind of expected because you have most people in some areas, but we're starting to rethink about what does this mean in the context of vulnerability when you have a large community of vulnerable communities in terms of the elderly, the sick, that are spread out across the whole island. To really get at that level of granularity, you have to go beyond just looking at municipalities. We really need to be looking at the individual street level assessment. So what we do is compute the number of days without electricity as seen from the lights. So what you're seeing here is the towns of the San Juan metro area coming in about 60 days. Here's the area of around Ciales and Adjuntas, the mountaintop region. This is Mayagüez and Ponce, the second most populated areas. And everywhere you're seeing what are essentially rural communities that have become isolated from many, many different factors. The high voltage lines cross from the south of Puerto Rico to the north, so you can see that Caguas gets power earlier. But areas like Utuado that are very disconnected, where you cannot even call 911, like even before Maria. This is not how it works there. It's very remote, very isolated communities that don't see the power gains. Now, this is not just an urban-rural issue. We also see a lot of discrepancies in terms of how much energy came in around the San Juan metro area. It's not like all San Juan lit up on one single day. And we start looking at the factors that drove that, like land uses, the kind of building structures, whether it's detached housing versus long-term multi-unit houses. So these are the kind of factors that we're trying to explore. So anyways, what you're seeing here is a new data set. And while it's just focused in Puerto Rico, we're going to be able to do this globally on a daily basis in near real time starting next year. So imagine mapping vulnerabilities in communities around the world, whether it's Syria or whether it's Rohingya refugee camps, vulnerable communities. We need to start rethinking our approach for disasters and disaster management to actually managing the risk. And to do that, we need to provide the data and the tools necessary for assessing these kind of activities. And that's it. Thank you.
Okay, thank you. And now we'll take questions from any reporters who are in the room. If you could please state your name and affiliation, I will come around with a microphone. Are there any questions from reporters in the room? Oh, okay. This way.
Mike Karlowitz from NASA Earth Observatory. This is for William McDowell. You were talking about the nitrogen load increasing in the past year and a half. Have you seen more blooms visible or not so visible in that area, or are you still waiting for something like that?
We haven't examined those images. We'd love to collaborate with people who have. And so the answer is we don't know if they've really been recorded yet. And it's beyond the scope of our particular project to be able to do that.
We have a question right here.
Hi, Liz Callagher from Environment and Energy at Physics World. Another question for William. Could you talk a bit about the mechanism for how the hurricane increases nitrate levels or variability?
Certainly. So nitrate levels in the stream, we have experimental evidence as well as general principles from the literature and other studies which show that both the supply of nitrate in the soils can limit and expand what gets to the stream, and then also the consumption. So what we see is that nitrate concentration in the stream is increasing due to both the increased supply as the leaf and other debris on the forest floor decomposes, and ultimately that produces a pulse of nitrate. And then we believe that as the trees regrow, of course they're using nitrogen to rebuild their tissue, and so that will tend to increase the consumption. So first we have an increase in supply and a decrease in consumption because the trees are damaged, and then those two get back into equilibrium.
Are there any questions on the chat? No questions. Are any other questions from reporters in the room? Great.
Maddie Stone, Gizmodo. This is probably for Maria. I was curious, you mentioned you had a number for for total tree mortality and carbon losses, and I was hoping you could put that in a little more context in terms of how many trees there are across the island and how big a fraction of the island's forest carbon budget this is that was lost.
Yeah, good question. So it's about a third. That kind of jives with the estimate that Doug gave based on remotely sensed estimate. I'd like to say that the 30 million trees, that has a very broad uncertainty around it, so it ranges from 20 million to 40 million. But regardless, it's a lot of trees. In terms of the U.S. carbon budget, it's about, if we think about annual sequestration, what came down is about 2.5% of the annual U.S. carbon budget in terms of sequestration in forests.
2.5% of the annual?
Of annual U.S. carbon uptake, yeah, in forests. That doesn't include grasslands and so forth.
Are there any other questions from reporters in the room? Are there any other questions on the chat? No? If there are no other questions from reporters, are you a reporter? Only registered reporters can ask questions, I'm sorry. Oh, okay, great. Okay, here you go.
So yeah, you mentioned winners and losers. Now I wondered what species won outside of the palms in this event. This thing could be considered management for certain species in a way. I'm wondering about the endangered Puerto Rican boa, or if they had benefited from more hiding places and open areas and so forth.
Right, so are you referring to animal species primarily? Okay, so in terms of winners and losers, so the winners are particularly in this storm, the palm, and also species that have generally flexible stems. So you have all seen those pictures that you see in storms where there's a reporter, and behind the reporter there's some tree, usually a palm, moving in the wind. So those are the kinds of tree species that do well in a storm like this. Historically, the trees that were really big and that had very hard wood also fared quite well in storms. This has not been the case in this storm. So this is the kind of stem breaks that I showed. A lot of those are big hardwoods that were broken. And as I said, we're not entirely clear how that happened. In terms of the cascading effects to wildlife, there are some of the, for instance, endangered parrots that live in El Yunque National Forest that were already under protection. They are under more severe threat right now. And one of the concerns that there is that they really don't have areas that are in good enough condition to serve as nesting grounds. For some of the birds, particularly the ones that live on the canopy, this is going to take some time to recover. For some of the anoles, lizards, and so forth that also require certain elevation to make their living, this will change the game. I don't know specifically for the Puerto Rican boas where they go in a storm like this, but this will have, and we have documented from previous storms, the impacts on various animals. But as I said, this storm is fundamentally different from what we have seen in the past. So the long-term ecological research side will continue to collect data over the next 10, 20 years, and we'll get a better sense for what this means.
Are there any other questions from reporters in the room?
Hi, Christy Taylor, Science Friday. Do we have any studies underway, this may be for Miguel, looking at how the environmental and the human disasters are interacting with each other? Human effects on the forest, or forest effects on power, things like that?
I think there's been a push towards understanding nature-based solutions to improve resilience and how they interact with each other. It's still at a very early stage. I'm not sure of a particular study I can point you, But one of the things that we're looking is at coastal resilience and how we're finally showing examples of how preservation of coastal lands has led to the saving of a lot of communities and lives. So you may look at work from Puerto Rico's Conservation Trust, where the entire conservation lands for Hacienda La Esperanza in Manatí, the local governments were fighting to put in 8,000 household units there, and they got a 10-foot surge from the sea. So that's 2,000 families that were saved right there. And so just the impact of visualizing the role that nature plays in protecting local communities. The same can be said about sand dunes around the northern parts and how it was just protecting a lot of the communities immediately inland and around Loíza and Isabela. There are a lot of local professors and universities that are working at trying to make that case. Yeah.
I might also just make one further comment on that, which is that many of the ecosystem impacts that were shown today, predominantly in state and protected forest areas, are obviously coincident with damages to vegetation in communities. And so those loss of vegetation in communities is part of the damage mechanism as trees come down on houses and rooftops in communities like the San Juan area, but it's also part of changing the microclimate and the environment. And this is something that NASA and our scientists are working in collaboration with colleagues at NIST, who are evaluating structural damages and standards, considering both the natural environment and the built environment. And I think that seems like a productive way forward as we're trying to understand some of the shared or even joint risk factors from a storm like Hurricane Maria.
Are there any other questions from reporters in the room? Are there any other questions on the chat? No? Okay, that concludes our press conference. Thank you very much.